Okay, cool. Okay, let's start. So from now on, seminars always on Monday morning. It's in the schedule. You don't like.
First lesson.
Yeah.
Right for sleep.
Yeah. Well, but maybe good then if you always wake up early in the morning is good for permanent rhythm. Okay, let's start. So this lecture, I will speak about standard optimal algorithm. It is a best algorithm to have small online mistake bound. And so it's best algorithm. And I will speak about perceptron algorithm. I will then explain about prediction and agnostic setting. I heard there was some trouble in the seminar, and then I will speak about perceptron algorithm again for for agnostic setting. Okay, so standard optimal algorithm. It is a very simple algorithm if you understand what is little stone dimension, and But first, let's recall what we did last week. So we spoke about halving algorithm. So if H is finite, we can take majority vote. And if majority vote is wrong, it means that from version space, so version space is a set of classifiers that are consistent with the given input-output pairs. And what halving algorithm does is reduce version space by half at each mistake. And so one can think whether the bound from halving algorithm, which is so algorithm says that maximal number of mistakes in a game is at most a logarithm of the size h. Okay, so let's do. Wait, I close the door. So let us recall what is the game. I will use in this lecture, I will use a slightly different game, but it's the same one. So let us say that now there are two players, predictor and challenger. And so challenger will start to give an input in each round, then predictor makes a prediction, and challenger can say whatever he wants. And the goal is for challenger to make a certain number, for a certain number m, to force predictor to make m+1 mistakes. But now, since challenger can make up any true labels, after he says m+1 times that the prediction is wrong, he must show a function from the hypothesis class H that is consistent with what he was saying. So if a version space is empty, so recall version space classifiers that are in H that are consistent with input-output pairs that are given. So if version space becomes empty at mistake m+1, then challenger loses. So he can say whatever he wants, but a version space needs to have at least one classifier. Okay, and so halving algorithm, whenever challenger decides to say wrong, it means version space decreases by half. And so he can say at most log h times that he is wrong. And in fact, we need to round down. We can round down and we get this bound. And so in last, okay, but this is not optimal bound. So we can have better bound. So let's look to the example at my right. So that's your left. No, at your right. Here is, so here the inputs are natural numbers starting from 1, 2, 3, and so on. And the set of classifiers are threshold functions. So there is a threshold t for example, 5. If the number is bigger, if the number is at least 5, then prediction will be +1. So note that sine, its famous function in machine learning, is equal to 1 if r is at least 0 and -1 otherwise. Okay, so note that differs from mathematical definition, because in math, in other areas of math, sine of 0 is 0, but we don't use this in statistical learning theory and machine learning. Okay, so here is the class of threshold functions, and so the claim is that so this is infinite size, infinitely many threshold functions, but there is a strategy to make at most one mistake. So do you know what is a strategy? So it's quite easy strategy. Yeah.
I thought of specific input, but it's not, we don't choose input, so it will not work. Yes.
Yeah, challenger chooses inputs. So if challenger and the answer is to always say -1. Oh, sorry. Yeah, this is one. Okay, sorry, I wrote down wrong example. Let us say each threshold goes to indicator. So that's not a threshold, but a singleton. Okay. This one is easier to understand the formula. By the way, mistake bound for threshold function is also 1. No, 2, sorry. Okay. Okay. Also in natural numbers. Okay, so this function, so each function in H of singleton classification, so each function in H is equal to 1 precisely on one point, and otherwise it's equal to 0. So here is indicator function. So x equals t is equal to 1 if x equals t and 0 otherwise. Okay, so now this is again infinite set because infinitely many thresholds, but mistake bound is 1. And so now it's easier to understand the strategy. So you should hear y is equal to 0, 1. So you should always say 0 unless you get a point that you've already seen, and this is the point where the true answer is 1. So when you always say 0 when you don't know the answer, then you will be good. Because once you're wrong in this prediction, you know what is a true function. So, okay. So that means that this bound is not optimal. We get infinite is smaller than 1. So there are also cases where halving algorithm is not optimal. So it will be for seminar. And so the question is, what is the best possible algorithm? And so let us think a little bit. And to understand this best possible algorithm, and let us think about the example of seminar. So there we had an example where the hypothesis, where the input set is finite. Hypothesis class contains all functions except one function. So it doesn't matter which function we take. So for example, we can take the all 0 function and assume that it's not an H. Okay, so let us look a bit more to this class. and represent all these functions on a tree. So we have three inputs, x1, x2, and so can organize these functions in a binary tree. Where the answers and so on. One more, this one we don't have. 1, 0, 1, and so on. And so here I have structured all the functions that are present in this hypothesis class H as a binary tree. All right. And we see for every leaf corresponds to one function in H. Okay. And so we said that halving algorithm will make two mistakes in this case, because H is equal to 1 less than 2 to the power size of X. And so do you know what is the strategy? So what's the strategy that halving algorithm gives? So halving algorithm will
majority from all consistent
classifiers. And in this case, so we have three inputs. So this majority vote will. So imagine that you have to come up with a strategy yourself. So how can you state a strategy yourself? Very easy. So we say that if we give it x1, x2, and x3, opponent cannot say 3 times 0. So our plan is to say 1 each time. And with this strategy, we'll make at most 2 mistakes, because we must be right at least one of the times. We cannot be wrong 3 times, because 0, 0, 0 is missing. So it's very convenient to make a tree for different inputs and only draw the branches for which the versions. So draw a tree, consider the game corresponding to the correct answers, and check the leaves that are non-empty. And so imagine, for example, that now we have removed this function. Imagine we remove the function 0, 1, 1. So imagine that this function is present, but we remove this one. So what will be the strategy? The strategy will be to always predict away from the missing leaf. So in the beginning, we see that the missing leaf belongs to the left branch. So we will predict the right branch. And then if we are right, it's good, because we've been right, so we can make at most 2 mistakes. And when we are wrong, then we are good by recursion, by induction. Why? Because if we arrive here, we know what to predict. So that's the strategy. Okay, and so now let me explain, before I explain what is standard optimal algorithm, I need to explain what's Littlestone dimension, and this requires concept of mistake tree. And a mistake tree is a very simple thing. It's just a tree in which the nodes are inputs. And there is one rule. So a mistake tree for class H can only contain nodes for which version space is non-empty. So every node, it's binary tree. Every node has either 0 children or 0, 1, or 2 children. So it's not binary tree. And we are only allowed to write nodes if input-output pairs for every branch. So the version space corresponding to input-output pairs on a branch is non-empty.
What is version space corresponding to input-output?
Yeah. So for example, when we look at this node, This corresponds to a game. So the game, for this game to see it, we look at the branch and we see that x1, 1 is an input-output pair from the first round. Then we have x2 0, because here we go left, and then we go left again. x3 0, we go left again. And we are only allowed to draw this node if version space of A, so if H consists a classifier that's consistent with these input-output pairs. So then elements of X times Y. So a mystic tree, again, is a tree, and all nodes are inputs. And it's only allowed to draw nodes if in the branch, the input-output pairs corresponding to the branch, if H contains a classifier that's consistent with the set of input-output pairs on the branch of this node. Okay, so that's mistake tree. So then there is a perfect binary tree. So that's a tree in which every node, so a binary tree, every node has 0 or 2 children. Perfect tree, it means that all leaves are at the same depth. So this is a perfect tree of depth 2. So perfect tree of depth D has exactly 2 to the D leaves. Okay, but this you've probably seen in some computer science course. And now I can tell you what is Littlestone dimension. So Littlestone dimension of a class H is the maximal depth of perfect binary mistake tree. So let us make another mistake tree. So it's not needed that on each layer the inputs are all the same. Or you can actually repeat an input. I could write x1 here, for example. But that's a bit silly because it doesn't help in our definition. We want a perfect binary tree. And when we repeat an input, we only have one child. Because in this node, we have to be consistent with all of the branch. Okay. Yes. So a perfect binary mistake tree is a tree that looks like this. So let us look to this example. So what is the Littlestone dimension in this class?
I have a question about the definition. So we like maximize among depths.
Yeah.
And previously you said that we can associate a mistake tree with the hypothesis class. So is there like many mistake trees
or H? Yeah, there can be several different mistake trees for
and we choose the one with the one which is a perfect binary and has maximum depth.
Yeah.
Okay.
Okay. So in this example, Littlestone dimension is equal to 2. And so, do you understand why? So imagine that there is a mistake tree of depth 3. The number of leaves of such mistake is 2 to the power 3 is 8. But we only have 7 classifiers. And so we cannot use the same classifier twice because
the tree will not be perfect.
Well, it will not be a mistake tree.
Oh, yeah.
Yeah, because the classifier can only be consistent with one sequence of answers. Okay. And so we conclude that little stone dimension of H must be smaller than log of the size of H. So its first property. So that's the argument we say. In order to have a mistake tree of depth D, we have 2 to the power D leaves in this mistake tree. And all these leaves must contain different classifiers. Because you cannot be consistent with 2 branches. If you have 2 leaves, then you look to the first point, the common ancestor, so you look to their deepest common ancestor, and there you get 2 different answers for the same input, which is impossible for same classifier. So they're all different, and little stone dimension is at most logarithm. Okay, so now we understand what is little stone dimension, and there is an easy property in the game we just considered. Mistake tree encodes strategy of challenger. So if there is a mistake tree, let's transform it to mistake tree. That I just removed one depth. So this mistake tree of our example here. So by the way, so this proves that here we have M of H equal to 2, because we found the mistake tree of depth 2. And yeah, so that's and we show that 3 is not possible. So we've proven this. Okay, what did I want to say? Okay. Mistake 3 encodes strategy of challenger. And so what is his strategy? So he will ask first input on the root, and whatever predictor says, he will say it's wrong. And so, for example, if predictor says 0, he will say correct answer is 1. And then the same, he chooses x3. If predictor says 0, he says correct answer is 1. And so number of mistakes he can enforce in this way is the depth.
That's always the same and equals to little stone dimension.
Yeah.
The tree is optimal.
Yeah.
And by the way, this is like not the tree which is for this example, because we
it works. So we have a function for x1 0, x2 0 is okay, but because x3 equals 1 is different from this function.
But why there are no any leaks, like or we want to draw like perfect tree, so that's why we cannot draw any leaves that are deeper.
Well, we can draw a few ones, but we cannot for all of them.
Yeah,
we cannot get 3 because we only have 7 functions. Yeah. But it will never work. So that means that challenger has a strategy to enforce 2 mistakes. And so we conclude that M of H must be
at least.
Yeah. So M of H is at least the little stone dimension of H.
Once again about mistake tree, am I right that we are not required to present like all elements of X? We just need like some of them, but if only if they're consistent. So in this example, we don't specify an output for X3.
Yeah.
But the branch, the very left branch is consistent.
Yeah, so in this branch, X2 is not specified yet. Okay. And so now we have a theorem that says that little stone dimension, that the mistake, that is M of H, the mistake bound, is exactly equal to little stone dimension of H. And so there is a really nice algorithm for it. So let me write it here. And that's called standard optimal algorithm. So here I wrote it. This is the title of this part of the lecture. So while true, get XT. See, so now we will look. So what is idea of algorithm? So algorithm receives input, and now it must predict a label YT hat, and it will look to the version space and add the pair xt yt to the inputs and look to these two cases, and it will look to two possible version spaces after receiving the next label. And this defines two, and so it computes the little stone dimension of these two spaces and picks the larger one. And this reminds me about this example with the missing thing here. Recall that we said the strategy was to always predict away from the missing leaf. And this way we can, if we are right, we gain something. But if we are wrong, then we will later gain something. In some later step, we are inductively guaranteed to gain something, because in the end, we can predict away from this missing leaf. So that's the same strategy. So the prediction will be the argmax of the little stone dimension. I hope it's readable. Say something. Okay, I will. Actually, I can write it bigger. Should just be more strategical. Okay. Say YT hat is equal to argmax of little stone dimension and so we consider all f in the version space T, for which f of, so argmax for the label y, such that xt goes to y. Okay, and it fits on the line. And now we get the correct label YT without head. Okay, so the only thing that we need to understand is this line. So here, VT denotes version space. All functions that are consistent with previously received input-output pairs. Then we try to add each of the labels. Then this reduces this version space to this space. Let's call this space, let's say that is equal to VT with some extra label Y. So for two choices of Y, it computes a little stone dimension and it selects the one with maximal little stone dimension. That means in this algorithm, it will always predict away from the one with the missing label, because so if it, for example, it receives x1, then little stone dimension of this version space is only one, because we cannot build a full binary tree here. We only have 3 functions in this version space, but here we have all 4 functions that are remaining. So this one has the largest version space, and we will predict 1. And so we continue. So in the other example with singleton functions here, so indicators of singletons, we do the same thing. We predict 0. Because if we, for the label 0, we will each time have infinitely many elements in the version space, until the moment we know which is a true function. If we put in the label 1, there will be only one consistent function. That's a function for which xt goes to 1. And so the largest little stone dimension of these 2 spaces is for y equals 0, always, until the moment that version space equals 1 element. Okay. And then the claim is that this algorithm achieves this bound. So number of mystics is bounded by little stone dimension. Okay, so what we will do is prove this claim. So now proof. So one direction is already here. So we need to write the other direction. Mistake bound is smaller than little stone dimension of h. That's what we need to prove. And so we will do it by induction on little stone dimension. So first, note that little stone dimension is equal to 1 if and only if h contains only one function. Sorry, little stone dimension is equal to 0. So little stone dimension of h is equal to 0 if and only if size of h equals 1. So this is easy to prove because of this upper bound. We know that so from this upper bound we get this direction, and for this direction, if little stone dimension h is equal to 0, it means that there is an algorithm that's always right, and that means that h can only contain. Sorry, what am I proving now? So I want to prove this thing, right? Mm-hmm. No, this we get from if little stone dimension is smaller than log.
That's the open.
Yeah, that's the. And now I want to prove this one. So if little stone dimension is 0, then it means that there is no mystic tree of depth 1.
So it's like the only node.
Yeah. So that means in the root, we can only go in one direction. And so we just build the single function in H. Okay. So this is clear. And yes. So then in this case, if little stone dimension is 0, then clearly mystic bound is 0. So we could say that little stone dimension of empty set. So for here to be formally correct, we should say that little stone dimension of empty set is minus infinity. So we will never predict a label that makes version space empty here. Okay. And then for the second step, we will say that at each mistake, little stone dimension of version space decreases by 1. So we prove this claim by induction on little stone dimension. Okay. So the stronger claim will be at any moment in the algorithm, the mistake bound of the version space, using normal letters, mistake bound is smaller than little stone dimension of VT. So that's invariant. So how will it happen? At each mistake, little stone dimension decreases by 1. And so we know that of version space. But this little stone dimension cannot go below 0. So the claim follows. Okay, so now so what we have to prove, so if there is a mistake, if mistake in round T, then little stone dimension of VT plus 1 is smaller than little stone dimension of VT minus 1. So that's what we have to prove. Okay, so we consider 2 cases. So consider these 2 subsets of version space. So this partition of version space. Imagine both sides have the same little stone have different little stone dimensions. So we have little stone dimension of VT, and the predicted YT is strictly bigger than little stone dimension of VT and the other one. So let's say not YT. So in this case, we are good. So we predicted the bigger little stone dimension. We are wrong. And then afterwards, when we make a mistake, we get that VT not Y hat is precisely the new version space. VT plus 1 is equal to VT not Y hat. And so we are good because it decreased by 1. So that's first case.
It always decreases precisely by 1, or may decrease
by more than 1, and then we are lucky that But in worst case, it decreases only by 1. And then there is case 2. So that these 2 have the same little stone dimension. But then I claim that this also holds. The same conclusion also holds. So that means I need to come up with, I will look at mistake trees from both classes, and I build a larger mistake tree, one more depth in the class version space T. Because version space at T is the union of version space of this version space and this version space. Okay, but that's very easy. So imagine that Challenger gave us here xt. And then there are 2 labels, 2 choices for y. And we know that we can build a mistake tree of certain depth d. So let us say that this is equal that Alden Vt y hat t is equal to d. Is equal to not y hat. Okay, so then I have xt here, and then I build here the mistake tree for this Vt y hat t, and here the mistake tree for Vt not y hat t. And so if this has depth d, then the full mistake has depth d plus 1. So this will be this is equal to version space t plus 1. So the one where we wrong. And so we see that the version space T plus 1 has one less little stone dimension than version space of VT, because VT contains both these sets. And so what we have proven is that in case 2, little stone dimension also decreases by 1. And so we have proven induction.
Once again, like plan of the proof, how the claim is follows, how follows from all of these other claims.
Okay, so we want to prove that this algorithm number of mistakes it makes is at most little stone dimension. And we do it by saying that each time this algorithm makes a mistake, little stone dimension of version space decreases by at least 1. Initially, little stone dimension of version space is equal to h, all the functions. And so version space is initially equal to little stone dimension of h. And at each mistake, it decreases by 1. And the smallest it can get is to 0. It will never go to minus infinity.
So it sounds very simple.
Yeah.
It's very similar to like the very first proofs, like when we have like projection coordinate functions. It's also decreased by 1 always. But
then we throw out the version space decreases by 1 function, and now the dimension decreases by 1. And now you know the best algorithm for mistake bound. And this is like the only place in statistical learning theory where there is tight separation. This is possible, one more is not possible. So all other bounds will have margins between best known algorithm and lower bound. But it's important because the idea of little stone dimension is connected to VC dimension. And we will later learn it for a more realistic scenario in machine learning. But then it will be mixed up with many other things. So I'm now presenting you all the ideas in separate form. So here is the idea of creating like a special combinatorial property that determines how many mistakes we make during learning. Okay, more questions. So then we have achieved first goal.
I'm just looking at
take your time.
At the middle of the proof. Like I get the idea, the plan, but it seems that the thing that we wanted to prove, like that it's always decreased at least by 1. It's the only like three last lines, and above we have m of VT less or equal to LD of VT.
Yeah, this is maybe not so useful. I should not write it. I just should say that number. Yeah. So formally, the plan of the proof doesn't need this. We just say at each mistake bound. But you can like say you can do this one time at the first mistake and then apply recursion.
Thank you.
Yeah, so it's a bit let's better stick to this plan. Okay, good point. So next thing what I will explain is perceptron algorithm. And I will again in realizable setting I will explain, and then I will go to agnostic setting. So let me clean the board. So by the way, we've shown that this bound logarithm of size of h is non-optimal, but we didn't show that there is a case where majority vote is non-optimal. And this is for seminar. So it's non-optimal, but it takes some effort to find counterexample.
You're speaking about weighted majority algorithm.
No. Weighted majority is for when you have infinitely many. You can apply with infinitely many that are somehow structured in many sets. And okay. So now let us look at mystic bounds. For the classifiers will now be half spaces. So what is half spaces? That means that X is Euclidean space with d dimensions. And the classifiers we can consider, they're all the functions that map X to X of V also in RD. Sorry, sine of this is regression function. Sine X times V and RD. Okay. So, and then there is some bad news because for this class, okay, let us say with d dimensions and mystic bound for is infinite. So it's infinite already for one dimension. So even the threshold functions, which I started to write, already have infinite VC dimension, infinite Littlestone dimension. So they have finite VC dimension, but this we don't know yet what this means. So okay, and why is this? Well, Challenger can do following strategy. So it can give, it can start with a point. So now let us look at threshold classifiers. So recall H threshold is all X that go to a sine of X minus T, the threshold in R. Okay, so this class, so in one dimension, so this has more functions. If D is equal to 1, this class has more functions because they're like thresholds on two sides. So thresholds of X and thresholds of minus X. So a half space in a line, it can have the ones at the right and the ones at the left. But here, the ones are always at the right of the threshold. Okay, and so how does it work? Well, we just start with any x1, and then if predictor says y1 equal to 1, then we will promise to put the threshold at the right of x1, so that is again, Challenger will always disagree with predictor, and the next time he will give a point x2 here. Again, there will be a prediction y2, and if it's equal to 0, he will promise to remain between x1 and x2 for the true threshold. So recall that the game I defined in the beginning of this lecture. So Challenger gives an input, predictor can say, predictor makes a prediction, Challenger can say whatever he wants to be correct or incorrect, but at the mth mistake, then Challenger needs to show a function from H that's consistent with his answer. And so he can do this. He can take a number m, repeat this any number of times. And here the set of consistent function is always an interval. I mean, maybe a half infinite interval in the beginning, but at some point it's an interval, and he can each time decrease this interval, but keep it non-empty by just disagreeing and promising to put the true threshold on the other side. After m mistakes, he can just pick, again, after more mistakes, for example, x3 will say here, and then the version space will be this interval, and then he can just pick as true function threshold classifier here. So in other words, m of threshold functions is infinite. And that means, but this is a subclass of all these classes for all D. I mean, okay, formally it's not a subclass, but I mean, by associating one coordinate and blah, 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 is essentially a subclass.
Special case.
Yeah. Okay. And so all these classes have infinite thing. But what we see here is that to play the strategy, like the intervals decrease geometrically. So when opponent, so predictor can always predict the label according to the border point that's closest. So if the right point is closer, he can say +1, the left point is closer, he can say -1. So this interval can decrease, but at most geometrically by 2 to the power t. So he kind of takes a majority vote on the number of consistent classifiers. There are infinitely many, but okay, you can measure them by looking at the interval, the new interval of consistent thresholds, and choose the biggest one. And so he can keep this interval of consistent functions to be at least 2 to the -t times some initial constant that he gets from the first two moves. Okay. So, but we can still deal with this. Our plan will just to create a promise. Challenger cannot ask about inputs that are too close to the threshold. So, for example, if the true threshold, let's make a new picture. If true threshold is here, then challenger, then there will be a margin, and the size of the margin is rho. And the rule is that challenger can not ask about inputs inside this interval of length 2 rho. And we will also limit the input space to an interval from -r to +r. So to deal with threshold functions. So to deal with threshold functions, we will set x equal to -r plus r, which is a subset of real numbers. And then promise that and then we get a logarithmic bound. So I'm just doing a bit of introduction for perceptron algorithm. What I'm explaining now, I won't ask it, just to understand a very important idea. So, so what I'm saying is that if xt minus the true threshold e is always bigger than rho, and xt is at most r, then number of rounds with mistakes, so number of mistakes is bounded by log r over rho.
Like the t's are not quite this.
Yeah, okay. Let us say s for the threshold. Yes, that's better. So S is true threshold. So in the game, at the end, when a challenger can choose the labels, but at the end, he needs to choose a threshold such that this condition is satisfied. And so then number of mistakes is R over rho. But this like covers this setting. And if you add one more mistake, you get for the one dimension. But now let us look at general dimension, and this bound doesn't work anymore. So for general dimension, so we want half space classifier. But now, what is this margin assumption? So now, for example, in 2 dimensions, we will have a line as true classifier. Okay, first we will always pick a line through the horizon, through the through the origin. And the reason we can do it is we can always augment the features and add to the whole input set a 1. And so bias term, so if this line is not through the origin, then we can use this extra feature that's always 1 to deal with it. So I explained it in detail in the lecture notes. Okay, so here is normal vector V. Here is the space. So here we predict +1, here we predict -1. And so the promise is that we will stay away from this border by at least a distance rho. So we will only ask, so x1, x2, x3. And in formal mathematical, we require that dot product with normal vector xt divided by the norm of this normal vector times yt is at least rho. So why do I multiply by yt? For example, if x3 is negative label, then the dot product with v and x3, so here is this vector, it's negative, x3 dot v. But it's okay for us because the label is also -1. By the way, we will use -1 and +1 as labels. So then this product is indeed positive again. So all correctly classified points, they call this the sign distance from the hyperplane. And then after we multiply by the label, then if it's correctly classified according to hyperplane V, it is positive. Okay. So, and now we can replace this condition by this condition. And here we will, in more dimensions, we will just take the 2 norms. So all norms are 2 norms. Okay, and now in d dimensions, so let me replace the definition. If xt times, so we assume that there exists a good hyperplane, so that this condition is satisfied. All norms are at most r, then the number of mistakes in general dimension is not logarithmic but quadratic. So it is bounded by r squared over rho squared. So this theorem, so the theorem says that perceptron algorithm achieves number of mistakes that is quadratic in the ratio r over rho. So that's our second result that we need to prove.
So the logarithm only happens to appear
in one-dimensional case. Yeah.
Interesting.
Yeah. Okay. And let me now quickly prove this. So I have time till 20 minutes left. Okay. But I still need to speak about agnostics, I think. No problem. We just need to hurry a bit.
In the condition, we must still multiply by yt, or
oh, sorry, yeah, it's a mistake. So, and now how does it work? So, like, naive idea would be like, by the way, this is the very first problem in machine learning that was ever solved. And so it's documented in the US. It's 1958, Mark Rosenblatt, he built first computer, so he had to invent computer for this. So he wanted to build a human that can see, understand, think, is conscious, reproduce, and so on. So, well, at least he wanted to do the beginning of this. And then he said perceptron algorithm is first step in achieving that. So he was very ambitious. And also in Russia, there was also a special place, only US and Russia, and it's called, so there were some math villages, all with very good engineers were together, but I don't find any documentation of what they were doing, but probably something similar. Okay. So, yeah, so we get some points. x1, let's say pluses when the label, and we get some negative points. So they're just negative. Actually, I don't need the names. And the question is, how can we find like efficiently a line that separates them? A naive algorithm would be just like to take the center of gravity, so like the mean of all the positive labels, the mean of all negative labels. So that's probably here somewhere. That's somewhere here, and then get a plane that's orthogonal on this. That's probably something like this. But it's not a good solution. So there are counterexamples, like this plus is wrongly classified, while just a while this line it works. So you can have like this is not a consistent rule. You can have a positive fraction of misclassified training points if you do it like this. Rosenblatt idea is basically greedy algorithm. It will go over all the points, and it will just adopt the points that are misclassified with the current rule so far. So he will build a vector WT that, so at time 0, this W is equal to 0. And then in every round, he will add up the input that is wrongly classified with the correct sign of the label. So he needs to find a WT such that X, the sign, is equal to YT. And so what's the plan is that if XT is wrongly classified, he will add XT to WT if it's positive and subtract is it negative. So that when it's positive, so if it predicts negative, but it should be positive, then by adding XT, this dot product increases. And so if WT plus 1 is equal to WT plus XT, then we see that the dot product of WT plus 1 and XT is equal to WT times XT plus norm of XT squared. Okay, I should say it in a picture, it's much easier. So, so we have a normal vector here, and imagine that there is a point that's wrongly classified XT. Then what happens if we add XT here? Then we get a point here. So then we will have WT plus 1 more in the direction of XT.
But still it's wrongly classified.
Okay, let's make it a bit bigger and then it's okay. So, and then his original plan is to cycle many times through the points and eventually everything will be correctly classified because of this theorem. So if a good classifier V exists, then the number of mistakes will not be too much. And so here, let's do the example here, and then we have WT plus 1. So if here is XT, then so each time we add XT when it's positive, we move it in the right directions. And if XT is a negative point, we will add XT y. Well, in general, we add X minus XT. So the rule is to do, okay, let's just write it and then prove correctness. Well, rule. Got XT, say sine WT times XT, we get YT is equal to get XT if you're correct. So YT equals Y hat T. Then we do nothing. YT plus 1 equals WT. And else we do what I say. WT plus 1 is equal to WT plus XT YT. So this algorithm Okay. And now we need to prove this theorem. So, and it goes into two steps. So we will look to this true vector, and we will say that each time we make a mistake, then after updating W, so first step is A, we will look to projection of T on this true vector. And we will say that it increases at each mistake. And each round with a mistake, we have two observations. First is that projection of WT with V increases. And it will increase by rho. And the second observation, okay, so there is an assumption. Know that we can scale V here. And so we will assume V is equal to 1. So unit norm. And second observation is that the norm of W grows only slowly at each mistake. So of course, in correct rounds, the norm doesn't change, plus R squared. And then this result follows by Cauchy-Schwarz inequality. So how do we get this? So we will take the square of A. So let us look at, so if M mistakes up to round T, then W T plus 1, sorry. Then let us look at so then we have that M times rho is smaller than WT plus 1 times V. So that's just A, I'm writing here. And so after M mistakes, the projection has increased by M times rho. So initially W0 times V is 0 because of initialization here. Okay, so then let's take the square of this and apply Cauchy-Schwarz. So this is norm squared of V, which is 1, times norm squared of T plus 1. WT plus 1 squared. And by B, this is M times R squared. So here is Cauchy-Schwarz. And here is B. Here is A. Okay, so now we can divide everything by M. So we have obtained that M squared rho squared is smaller than M times R squared. And so now we rearrange divide by M and rho squared, and we get that M is smaller than, okay, we just get this. M is smaller than R squared over rho squared, and we are finished. Okay. So this is proven. No, I have to say why A and B are true, yeah. Sorry. Yeah. And so why is A true? And that's just by definition. So just by the update rule, we are in a, so we have WT plus 1 times V. We just insert WT plus YT XT times V. like this. And then we look at the assumption here. So norm of V is 1. And so we just apply this inequality. This is star, and then apply star. Okay, I don't need to write it, it's clear. And then for B, it's also by, here we use assumption that this sign is wrong. So let us write it. Again, substitute definition of WT. So we have WT plus XT YT squared. Now expand, let's expand WT squared plus 2 times W dot product XT YT plus XT squared. Okay. Now we know that this must be negative. So why? We know that this product is different from YT. Means if we multiply the sign with YT, we get something negative. And so the sign of this thing is negative. So per thing is negative. And that means if we drop it, we get an upper bound. WT squared plus, and then we also get an upper bound for norm of XT squared from assumption here. So we're done. So this is proof of B. Well, it's really cool, but it took some time before people realized this. And even more amazing is that there exists a modification of this thing for agnostic setting. And it was only 2008 or something by Mori, the guy who wrote the book that we will use in October, November. At least the course uses a lot of inspiration from this book. So in the last 6 minutes, let us quickly say what is agnostic setting.
Can I ask a question about this? So the bound is not optimal. So we still get optimal bound as little stone dimension of.
Well, here is margin assumption.
Oh.
So this little stone dimension doesn't work.
Hmm.
It's a weird assumption. Like the input space depends on the true function. Yeah, and so we cannot apply. Okay, more questions.
Are there any results about optimal bound?
Yes, in seminar that was supposed to be in previous
yes,
seminar.
I remember that.
Yeah. A case where this is tied. So it will be a next seminar. Okay. So now let's speak about, so here we have assumption. What happens if we drop this assumption? So in agnostic setting, it just, okay, I will say later more formally, but here what we do is we just drop this assumption and the labels can just be anything. And then we still have a nice bound on number of mistakes. And it is given by sum over all rounds T equal 1 to, let's say big T is, and then it is 2 times the maximum of 0. Yeah, I need more space. Okay, I will remove this part. Number of mistakes is at most R squared over rho squared plus sum over T equals 1 to T of 2 times maximum of 0 and 1 minus yt xt times b. It's new theorem. Okay. So to prove it, I will follow the structure of this proof, exactly the same, just a few modifications. First, recall that I can change rho. I will use 1 over rho here for norm. And so what happens with this equality is that this becomes a 1. So why? If we look to this proof, we have here, we need to divide by the normal phi here. Sorry, yeah, here divided by the normal phi. And this is equal to, so here we have, sorry, Wt times V plus rho divided by rho. So this is at least rho, and then we divide by normal phi. I'm confused. Okay, so I am just, okay, it should be something like this, so there should be a 1 here. This remains the same. And then here, when we apply Cauchy-Schwarz equality, we have the normal phi again here. And so there will be so there will be no rho here, but it will be so we will have m times rho squared, and then nothing changes. No, 1 over rho should be here. 1 over rho squared, and here we have 1 over rho squared. Okay, this is the structure. I will hurry a little bit so I can finish this part, and everything for theory on perceptron is finished. Okay. So now I need to discuss what changes here. So this is basically the same proof with a different scale of V. Okay, it's a bit scary because something is wrong here, but I clearly remember there should be +1. Okay, let's deal with this. So basically we make rho much bigger, or yeah, depending on what you mean by bigger. So what we add here is, no, we don't add V here. We just have to look to, so here was assumption that xt times V divided by normal phi is bigger than rho. So, and if we clearly, if we say that rho normal of rho times V is 1, so when we put it here, we get plus 1 here.
But we get rid of this assumption.
Yeah. But I'm just saying that we will adapt this proof here, and to make the connection clear, I want to have the version that has 1 here, because we will compare it with max. Okay, so just this thing is not here. It was just a small reformulation of previous problems. So now we will go back to the theorem in agnostic setting, where we don't have this assumption. Okay, so now what changes in A and B? So we will use the same structure, but now we will here subtract maximum of 0 and this thing here. 1 minus yt xt times v. Okay, so so now we have to do 2 things. We have to prove that A and B imply this bound. And it will be very similar. So let us call this thing. So we want to, okay, first step, we need to adapt A. Let's start with proving A. So we get yt xt dot product v here. But what we have here is that if the maximum is the second element, we have again precisely the same thing, ytxdv here. And so then we have equality. So if the maximum is the right-hand side, but if the maximum is 0, then we subtract the maximum. So it can only be something lower. So this bound is better than we had previously. Okay, but let's not. So this bound is very easy to prove. Yeah. In this proof, nothing changes. We only use the update rule, and this hasn't changed anything. So we are good. And now let us put things together. So let us sum this over all the rounds with a mistake. So what we get then here, we will have that at round WT plus 1 times V. It is equal to M for the number of rounds with the mistake. So assume again there are M mistakes up to round T. And we have this M times 1 minus the sum from max 0, 1 minus YT XT times V. T equals to 1 to T. And we have an equality here. Okay,
How is the thing?
Just summing this over all rounds with a mistake.
Oh, okay.
So we assume M rounds have a mistake, so this one becomes M, and then we sum over the maximum. Okay, let's now call this L. Let us say that this is equal to L. So then let us look to the square, T plus 1 times V squared, because we want to apply Cauchy-Schwarz. It is bigger than M minus L squared. And so let us write this M squared minus 2ML plus L squared. So this is smaller than this thing. So I remove the plus L squared, so it only becomes smaller. Okay, on the other hand, we know that this thing is bounded by, we apply Cauchy-Schwarz again. So normal V is equal to 1 over rho. So we get 1 over rho squared times norm of WT plus 1 squared. And then we have this bound B. By summing this, we have M times R squared. And I forgot 1 over rho squared. So what's conclusion? I have a bit of space here. Conclusion is that M squared minus 2ML is smaller than M R squared over rho squared. So we can drop M. And what we get is M minus 2L is bounded by R over rho squared. So we just need to move 2L to the right, and we have this bound, because this is L. This is 2L.
A lot of calculations, that was complicated.
Yeah, yeah. So, well, basically, you just have to work out the square, and then you're good.
And all this written in the lecture notes, I guess.
Yeah, yeah, in detail. So just a little bit of extra calculations. It's quite natural. It's a miracle that nobody realized this. It's the first machine learning algorithm ever. It was important, and until 2008, nobody realized And it's just a few equations. Compared to other papers people write, this is nothing. Yeah. Oh, very nice result.
And so want to ask, so diagnostic setting, as far as I understand, is like about hypothesis class, that we don't have true classifier in it.
Yeah.
But we just got rid only of one assumption, of margin assumption, and we didn't say anything about.
Yeah, I didn't say, so there was confusion in seminar, at least what it told me, his name, okay.
Seminars.
Yeah, the seminarist told me there was confusion about the definition of H.
Yeah,
Yeah.
it's complicated.
Okay, and so it's a game, and so there is no true function, but it's similar as a game I used in this lecture. So in the lecture notes, there is no game, just something happens and some condition must be satisfied. But if you want a game, then it's two players, predictor, challenger. Challenger can give any labels he wants. And then, so when when we want to say that this is equal to S, and so when he says m+1 times that predictor is wrong, no, when he says S times predictor is wrong, so when challenger says S times predictor is wrong, then he must show a classifier from H that makes at most m mistakes on the history of given input-output pairs. So special case, exactly m mistakes, sorry. So he must give a classifier that makes m mistakes. And so m agnostic is 0.
Just m.
Yeah, in the realizable setting.
So we allow to challenger like make at most or precisely. I assume that it is at most mistakes as far as I remember from the action.
Yeah, at most mistakes. You're correct.
So in this perceptron theorem, we use like this performance measure, or like we just spoke about number of mistakes in this theorem.
Yeah, in this theorem,
we just bound number of mistakes, and the difference, the whole difference between this theorem and previous one is like the absence of margin assumption, right?
Yeah, here is no margin assumption, but here is also no fixed number. So the thing is that this doesn't give a bound on m agnostic here. And the reason is why, mean that consistent V might exist, but it can get arbitrarily close to the margin. So that means this get arbitrarily close to 0, and you're punished for correct predictions. So this bound can be infinite, even though there are 0 errors by perceptron algorithm. So it's on the upper bound on numbers, and this upper bound has no meaning. But if there is margin assumption, if all inputs are far from the border, then you can have, if you scale V correctly, then the maximum will always be 0, and you do get so under some assumption. So you do get in some sense a bound. But okay, margin assumption you cannot put in this definition because inputs depend on the true classifier. Okay, but we are 10 minutes over time, so let's close the lecture. Unless there are more questions. So there is something in Telegram, I think. Ah, no.